My name is Russ Kirshner. I'm a senior engineer at DevTools at NVIDIA, and Jeffrey Keel is a senior manager here in the same group. Mostly here to talk about DXR tools today. First, the thing on the agenda, we want to give you just kind of an overview of our tools in general, how they fit together and interlock with each other, and then get into the DXR specific things, and finally finish with a new feature which is more broadly applicable, which is crash handling. So I think as developers, we all generally kind of bounce back and forth between two concepts, debugging and profiling perf work. And that happens to be, the convenient split in a lot of our tools as well. On the debugging side, we've had traditionally a lot of frame debugging to inspect your API. Again, we're going to introduce NVIDIA Aftermath, which is crash debugging. And then we also have our profiling side. Oh, we're not getting any slides.
Sorry. That's my fault, not his.
OK, so yeah, that's what the debugging slide looks like. Sorry about that. This is our profiling side of things. We have it segmented into, first of all, Nsight systems, which is a fairly new tool in the past couple of years, which handles both CPU and GPU profiling, and moreover, you can see the two side by side, which is kind of how you want to see them. We've got GPU trace in the middle top there, which is going to be warp profiling. We've got the range profiler is kind of more of a global view of counters on the GPU. And then coming soon, brand new tool, which we're going to show a little bit. It's the Nsight Graphics Shader Profiler, which we kind of brought up specifically for DXR because traditionally you could get so little visibility into a ray tracing call with the many subcalls that generates. We thought it'd be really nice to provide you with a way to look inside that and see what's happening. OK, specific to DXR, we've developed some brand new tools in the past couple of years. A quite obvious one is the acceleration structure viewer. Since you now have all of your geometry globally at once, you want to be able to kind of traverse that, understand it, break it down. And that's our goal with that tool. One of the first things we brought up was the shader bind table view that unpacks all the binary data so you can click into your shaders, see what the resource bindings are and their specific arguments. And then, GPU view, again, is very useful for looking both at the acceleration structure building side as well as the dispatch side. And then, crash debugging is good for everybody. And this is the demo Justice. You can actually see this running in the NVIDIA booth right now. It's actually pretty impressive. It was this developer NetEase that within the span of 2 months, they start out with a DX11 demo, and they not only converted it to DX12, but also added RTX within that span of 2 months. I couldn't believe the schedule that they made with that. But like I said, you can see it at the NVIDIA booth if you'd like to know more about the demo specifically. Today we're going to be working with a little bit earlier drop of the demo. It doesn't necessarily have all the final bug fixes or perf changes, but it was interesting to talk about some NVIDIA debugging with this. Now I'm bringing up our combined CPU-GPU profiler Nsight systems. Right here, we've just got a static screenshot of Justice. However, I wanted to talk about a larger capture for a second because we've added some new features since I made this capture. Yeah, so it has a lot of the same features that we had in earlier versions of NVIDIA system profilers. You've got command list recording, and you've got execution, you got GPU workloads. You've got visibility into threads, what they're doing in terms of their kind of occupancy on the CPU. But one really nice feature that's been added lately is frame health. And you can see those kind of red bars that are scattered all over the frame there. Those show you basically this idea of like, okay, compared to the surrounding frames, how good was this frame? Like if this frame was significantly longer than the frames that surround it, then we mark that in red so you can just focus on that without having to like manually hunt and peck for it. And then furthermore, within there, we'll determine reasons. So we'll say not only is this frame longer than the surrounding frames, but we notice that the map unmap in there took up a really long time, or your shader compiles took a really long time within this frame. And that zeroes in on what you really want to optimize kind of on the CPU side of things. In this particular frame, you can see that there was a stall that was due to map. And you can see that affecting the CPU, and then down on the bottom row, you can see how that percolates down to the GPU and causes a stall there, and no work gets done. So you can kind of quickly see how this could save you time. Kind of going back to the slide with Justice, there were two particular perf markers that we wanted to focus on. We've got the update, which is full of a bunch of build ray tracing acceleration structure calls, as well as ray tracing reflection, which is the most expensive dispatch raise call within the frame. And you can kind of see their cost both on the CPU side and then down below on the GPU side. So that's what we're going to try to fix in this demo. Whenever we're tracking down a performance problem, it's really nice to be repeatable and minimal, and not have to load your entire app and have all this variability that might occur with other things happening besides your graphics rendering, and just isolate what you care about. So one feature that we've had for a while, and we've extended it to DXR, is a C++ capture. Basically what we do is we do one of our live frame captures with Nsight, and then we convert that serialized to C++ code, a bunch of C++ files plus one binary data file to go along with it. And as you can see here, there's like standard launch options that occur with all our different activities, but they also apply to C++ capture, so command line arguments, environment, et cetera. And then after you do the capture, the output is going to be what you see on the right, which is a summary of the C++ capture, a screenshot of the correctly rendered image, so you can compare and make sure you're getting what you expected when you do the replay, and some other metadata. And this is a more expanded view of the C++ capture widget. What you can see is that within this widget, you can build or run or even like execute or connect to another activity on Nsight. So in other words, you can C++ capture, get that output, compile it, and run another frame profiler, or even you could do another C++ capture if you really wanted to, all without leaving with this widget. So it's all very streamlined for kind of iterating along with the output that you've just made. And now that we have the C++ output, I'm going to hand it to Jeff, and he's going to talk about what he did with it.
Yeah, so what we did was we looked at the frame and we said, we've got this ray tracing reflection section here where it's one of the dispatch rays, and we were wondering, why does it take so long? So let's go ahead and use the range profiler to figure it out. Now, for those of you who have seen the range profiler before, you may say, oh, come on, I've seen this demo 3 or 4 times. Jeff, there's nothing new here. I'm tired of hearing you talk. But there is something new here, and that is we've got a new range profiler that is actually user configurable. So rather than having all pre-canned sections and everything with all the data, this is all user configurable, which I'll talk about a little bit later in the talk, but I just want to give you that heads up. So what we did was we came in and we said, okay, this is our big dispatch, and I'm going to go ahead and profile that dispatch and get a feel for how is it utilizing the GPU. What are we going to see here? And remember, Louis Bavois put out a great blog article about how to use the range profiler and how to analyze the data that you see there in order to be able to understand how things are utilized in the GPU pipeline. He calls it the 3 Ps, the perfect, I can't remember. Anyway, but it's a really great blog article. I encourage you to read it. We've got a link to it later on. But the idea is you come in and you look at what you've got here in the top SOLs or top throughput metrics and get a feel for where am I more throughput bound along the GPU pipeline. And we can see here our SM is only about 10%. So I'm actually not seeing a whole lot of a whole lot of throughput happening on the SM. And then that story kind of continues here. In terms of my SM active, I'm about 92%, so it's fairly decently, the number of clocks that it's spent active is pretty high, but my throughput per active cycle is only 11%. And then I look at my occupancy, and I'm looking at like only 38%. And so I'm starting to see a story here that I'm really just not taxing the SMs very much. Last one you can also see is look at SM active threads per instruction executed. So basically how many threads were active for every time we're executing an instruction, and it's only 42. So we're looking at some very low values. The kind of the general story that we're seeing here is that the GPU is not occupied across the entire time. I think we go back to you.
Okay, and I also wanted to point out that in terms of RTX, we're offering you tools, but that's not all that NVIDIA is offering. We also, put out a brand new tips and tricks, best practices website, actually right now with GDC, by Alex Dunn, and it's got way more information than this. It's got a nice table of contents outline, things separated into categories. But I just brought out 4 basic examples of the types of things it says. And in particular on this talk, I'm going to kind of focus on this concept of merging bottom-level acceleration structures when possible. And there should be a lot of heavy emphasis on when possible, because it's not something that's always going to generically work. There's metadata that's associated with instances that you could lose if you try to merge too many things, or you'll have to figure out how to refactor it, basically. And then the other, this is kind of a generic D3D12 tip, but batch your barriers, always batch your barriers. And what we found with some early applications is they were putting a barrier between every bottom level acceleration structure, which isn't needed. You can actually build them in parallel, get them all done, do a single barrier, and then build the top level structure, and then render. And then also preferring opaque geometry gives the hardware and drivers some chances at optimization. Okay, so we have captured live this C++ replay, and we've opened up the frame debugger and gone in. Did we type raise on the events view as one way to navigate to it? Yeah, you can see that brings up a quick filter. The first one is actually the one that we're concerned with. And it brings over the dispatch raise page on the right-hand side. You can see a few different things here. Like you've got the basic launch dimensions and basic metadata, but it's also got the shader bind table exploded, which is, if you've already developed for RTX, is a pretty nice utility to have. It's really easy to get wrong. But you can see, yeah, we've got hit shaders, ray generation shaders, and for each of those, you can go to the link for the shader. You can see the texture and buffer resources for that particular sub-shader within the dispatch raise. And finally, we have acceleration structures. We detect the bound acceleration structures. So since that's what we're kind of interested in debugging, we'll go to that. So you can see the entire scene's geometry for justice right here. And roughly, like every single color corresponds to a geometry mesh, which is 1-to-1 in this particular example. Geometry meshes and instances within the top level structure. We've got some nice filtering and highlighting over on the right-hand side. I just talked about that tip and trick that you want to make everything opaque whenever possible. And what you see, if you check non-opaque, everything stays highlighted. It doesn't gray out, which tells you that everything is non-opaque. It's probably not a good situation, assuming that you're not doing that many tricks with any hit alpha type effects. You probably don't want that. So that would be an easy optimization to make. However, the things I really want to call out are over on the left-hand side, specifically. Okay, we're actually looking at the later version here.
Yes.
Yeah. Okay, so what I want to call out on the left-hand side is like we actually had 1,500 instances. We're kind of peeking ahead here, but it shows 2 instances there. It was originally 1,500 instances. And you can see the geometry prim count over there. Some of them are 46, 52. Some are slightly larger. But we're really not, when we're building the bottom level structures, we're not really giving the driver very much data. It's not an optimal situation. So that's something that we're going to want to look at addressing. Okay, so one thing that we know from driver folks and dev tech is that high number of bottom level structures impact both the building side on the GPU and the CPU, as well as on the ray tracing side, or basically the traversal operations the GPU has to do will tend to be more complicated, less efficient, if you don't give the driver larger batches of geometry in the first place. So our goal is to reduce the number of blast builds. There's other options we can take, like building the blast on the async compute queue, which, by the way, you should see Louis Beauvois' talk tomorrow on Friday. He's going to talk about that extensively. And then there's these other tips like marking everything opaque, but I found that was a very small speed up. So maybe making these kind of modifications are easy in your engine or app, or maybe it would be more convenient to use the Nsight C++ capture that we already generated for you. This is a fairly new feature that we've exposed in our C++ captures, which is a simple concept. Instead of just literally writing the function names for the serialization, we have these my_shim wrappers, which I think the utility is fairly well known and transparent. The approach that you would take to design your own experiment would be to copy over something from the H file over to the CPP file and actually define it as a function, which is exactly what I've done. I've defined an override for build ray tracing acceleration structure. And I tried a few different approaches, but what I kind of settled on was, okay, let me go through the scene. I can see all the build ray tracing acceleration structure calls that happen in the frame, and so let me collect those into a dynamic pool and create a single blast with that. And then the remainder, I assume, is static, and I create another blast with that. And then I merge the two together with a top-level structure and render with that and see what I get. And I got something, and it was actually quite surprising because we were seeing like close to 10x or around 10x speed up with the dispatch raise call, and I said I want to believe that following NVIDIA's guidelines got me something, but this felt like too much, and other people within the organization said, wow, do you quite trust that? And I tried verifying on various tools that we had, and I wasn't quite able to put my finger on it. But Jeff is going to help me out again.
Yeah, so we worked together on this. We were kind of scratching our heads. We wondered if we'd finally found the unicorn, right? I mean, the 10x speed up, that's something that everyone would love to be able to do. So what we did was we ran the range profiler. And we said, hey, GPU, tell us what's going on here. And remember that before it was like 2 point something milliseconds, and now this section is like 0.18 milliseconds. So it's significant savings. And then we looked over here. Now our SM active is only about 26%. Okay, SM throughput's looking good. I mean, all these numbers were looking pretty good. Even the active threads is now 85%. So we've doubled the number of active threads. So we're thinking, this is really great. But then we started to look at the RT core metrics. Now the RT core metrics are something that are very special. They're only available in what we call our Pro product. And so the idea here is that if you join our Pro program, one, you get early access to builds and different features and everything, but then also there's additional metrics that we can give you inside the GPU so that you can gain additional understanding in terms of what's happening. So these are some things that are only available in the Pro. So this is the new ray tracing section. This is one of those sections that I created. And you can see here that our one ray trace call that we've got here, but we noticed that our intersection throughput was 0. And our intersection ops was 0%. And then went even further and looked at the actual breakdown of the intersection ops, and there was basically no intersections going on. And so then, of course, GDC came, and so we had to stop all of our development. So we haven't actually solved this problem yet, to be honest. But the cool thing is we were really able to use the tools to say things aren't quite what they seem to be. So what we're going to plan on doing is we're actually going to go back. He's going to go to Florida. I'm going to go to North Carolina. I'm going to put our heads together and try and figure out exactly what this puzzle is, again, utilizing those tools. And we're going to kind of finish the story from the slides. So we'll go ahead and give you that when you get to download those slides from the internet. And then I guess I could go a little bit more into the range profiler, kind of the configurable capabilities. All right, cool. So what I want to do is also show you, and I'm going to give you a quick idea how this works. I'm actually going to do a talk literally coming up right now, the next talk tonight. And it's going to be on Vulkan, but it's the exact same capabilities that you've got. And I'm going to go a little bit more in depth into one, how to understand the metrics in the range profiler, and two, how to utilize it. But just to give you a basic idea, again, rather than having all these metrics be kind of pre-curated by NVIDIA, and like that's all that you can do, although you have the user metrics section, what we've developed is this concept of a section file. So this is a text file that, one, we supply, but then also you can make edits to, or you can create your own sections. And you can basically say, okay, in the header section, which is what you'll display up here, you can say, here's the different metrics. This is actually from the SM section right here. So I've got like SM active and XM active, mix, min, max, delta. So you can see these right here. And so I can specify exactly what I want there in the top section, and then all of these can have a body as well. And actually they can have multiple bodies, it turns out. And so I can have different tables, I can have, like we showed over here, I can have different histograms, I can have different graphs and everything like that. And you can specify those down here in the body section. Now the other thing that's really great about this is we actually allow you to write what we call rules. And so the idea here is that in a Python script, I can go ahead and sample values out of that database of values in the metrics and say, hey, if this value is greater than this, if this value is less than this, put up a little message. And so I had a very simple one here. I just looked at the draw count and dispatch count. I said if I have more than 5,000 draw calls, put up a warning and say I've got a large number of draw calls, and then just put a simple information that says more draw calls or more dispatches. And then you can see here I've got my little information section here. And it's all editable on the fly. So I can say, right now we're in the more dispatches than draw calls. I can say, put Bob in here and hit Control F, and you can see, well, it didn't auto-load for some reason. No, that's why. Oh, it's got the read-write permissions is not set right. But it goes ahead and automatically will load that up for me and dynamically be able to do those edits and everything. So again, come to my talk next coming up. I'll go a lot more in depth on this and give you an idea of how you can utilize it. Oh, wait a minute, there's one more, right? I'm going to do slides next, right? Yeah, okay.
Yeah.
So the next thing I want to talk about, so the other capability that we've got from the profiling perspective, and this is starting out in RTX, but then it's also going to go towards rasterization and some of the other shader types that we have, is a shader profiler. A lot of times what happens in the shaders is as they're being executed, they're going to be either have long paths in the GPU or potentially be reading things from other areas inside the GPU from like the texture unit or reading things from global memory. And so what the shader profiler gives you is feedback in terms of why those warps are stalling, why they're not able to issue instructions. And so this is something that literally is hot off the presses. My fingers were burning as I was making the slides. But we basically give you an idea of for every single shader that you've got in your scene, in this case it's the DXR shaders, one, you can look at which one has the most samples, because that's going to be your hot spot, right? That's going to be the shader that's used most frequently. And then you can see the breakdown of all the different reasons why we had stalls. And so here's a great example of looking at one shader. We can see here that most of them was stalled about 42% of the time on short scoreboard. And so short scoreboard is going to be reading something from a memory unit that is not the texture unit. So it could be from global memory, it could be from basically anything that does not go through L1 text. And so long scoreboard is when it's reading something that's coming out of the texture unit, for instance. So again, basically on a line-by-line basis inside of your HLSL shader, you'll be able to figure out exactly what my stall reasons were. And again, if you're in the Pro program, you actually will be able to see that for our low-level assembly language, which we call SAS, and you can actually see that as well as part of the Pro program. So again, all these things are capable if you join our Pro program. I'll turn it back to Russ. Oh, no, it's aftermath. Golly, yeah. I keep on forgetting where we're going. All right, so the last thing we want to show you, we're coming back more to the debugging side of things. So when we talked about earlier, we obviously have the frame debugger that's been available for quite a while for API debugging. But we got feedback from developers saying that, one of the key problem issues I have is that I keep on hitting GPU crashes or GPU exceptions, and I have no idea why. And so we kind of put our heads together and we said, okay, we don't want to have people seeing these nasty blue screens and little pop-ups that come up and warn them about things that are happening in their GPU. We want to be able to give them an idea of exactly why they're hitting that issue. And so what we did was we developed Nsight Aftermath. And so we actually first shipped this for DX12, I think it was in January. And then for GDC, that version, we're actually shipping support, including support for DXR shaders. And so this is an example from one of our samples that we have of when you hit one of those crashes, what's going to happen. So the idea is when you hit the crash, you will actually generate a core dump on the GPU, and that's going to give you all the information about why that exception or that crash happened. So you can either use a command line utility to be able to kind of spelunk through and look at the reason why it happened, or you can load that crash dump inside of Nsight graphics, and then you can see all the information kind of graphically and visually, which is great. So when you first come in, you're going to see the dump info, which is basically, you know, what was running when I had this crash, what the application was, what type of an exception it was. In this case, my GPU was hung. So I had something that was hanging the shader units, or at least one of the shader units, and then information in terms of what system I was running on. But when I click on the crash info, that's going to give me all the information about what was happening inside the GPU. So I can see what the GPU state was, which units were busy, which units were idle. One of the other capabilities that we give in Aftermath is the ability to put breadcrumbs or markers in your application so you can hone in on exactly which draw call or dispatch caused the issue. And so what this is doing is this is basically showing exactly where those breadcrumbs were decorated throughout our application. Now, the other thing it allows us to do is actually see a call stack from that so that we can, again, figure out exactly where, because obviously our engines are not like these big linear programs. If they are, you're probably, you know, scratching your head and trying to figure out why it's so difficult to write it. But, you know, you've got lots of different loops and all that kind of stuff, lots of different objects in your application. So now you can actually see your call stack for that. Once we get things finished with loading all the PDB information, you'll be able to actually link to the source information. So it's great to be able to figure out exactly where it's happening in your source code. But then also, you can actually see where things are happening in your shader code as well. So in this case, what we did was we put in a simple little infinite loop here, and what happens is that this basically shows me what PC I was on, what program counter I was on when this actually was hung, and it basically sampled that from all the different SM units, all the different shader units inside the GPU. So again, great to be able to kind of hone in on where these exceptions are happening. Now, along with this, we've got a kind of a couple of different levels that are going to be available. What we're showing here is what we're calling level 1. The idea here is that there's no code instrumentation. You don't have to do any code instrumentation. You don't have to do any changes to your program. On the left-hand side, you see that dialog right there. All you have to do is just simply whitelist your application, and then we will go ahead and be able to harvest any of the dump information that comes if you happen to hit an exception. That's just called our Aftermath monitor. And then it just generates the crash dumps. You get all the exception information, all the shader state, all the application details, and that's available in the dump. Now, level 2, and this is something that's coming, what this is going to allow you to do is actually launch your application as an Aftermath activity. Now, you remember earlier Russ talked about these number of different ways that you can launch your application for profiling or for debugging. Well, now there's actually going to be an Aftermath activity, and what that's going to allow us to do is that's going to allow us to auto-instrument your application, and you'll be able to control the level of instrumentation. So if you're using either NVTX or any one of the other perf marker APIs, we'll obviously instrument at the perf marker level, but then you can also flip a bit and say, oh, I actually want every single draw call within that perf marker level. So rather than you having to like make modifications to your code, add all the tracking for Aftermath and things like that, we'll automatically do that for you. Now, the other thing we'll allow you to do, other thing we'll do for you is resource tracking. So if you have like an MMU fault, say you've got a resource that was deleted before it was actually used, we'll actually add the resource tracking for that automatically so that in the dump file, we'll actually print out the ID of that resource, and then if you used any one of the debug APIs to name that resource, like, you know, the diffuse buffer from the gbuffer pass, then it'll go ahead and show that as well, so you'll know exactly which buffer it was that caused the MMU fault. You want to take this one? I'll take this, or? I'll take it, sure. I'll finish things out then. So Nsight Graphics 2019.2, go download it now. It's available. We went ahead and shipped that. It included, again, DX12 and DXR profiling and debugging. We got the new range profiler. It's in a preview state at this moment, so we definitely would appreciate your feedback. And actually on the right-hand side, right-hand side, you'll see that dialog. This is actually another one of the new features for 2019.2, and that's the ability to give us feedback directly within the application. So in the upper right-hand corner, you'll see a little, kind of little comment call out. You just click on that. You can include different information, including some basic text. You can include an email. You can do a screenshot. Any information you want to give us that'll help us to understand either the problem or the feature that you want us to have, and we will get that feedback, and we will definitely contribute that to our database in terms of feature requests and bugs. Nsight systems for DX12 and Vulkan, we're actively finishing things up there. It's going to be shipping shortly. And then again, I encourage you to join the program. Go ahead if you want to join it. At the last slide, we'll have an email in terms of Nsight Graphics at NVIDIA.com. You can send an email to us there. In order to tell us that you want to join the program. You're also welcome to come up to us afterwards. I can give you a card, and you can contact me when we get back from GDC. But we definitely encourage you to do it. There's lots of great information in the pro side of things that are not available in the public tools. And with that, I'll ask for any questions.